Hi everyone, this is lecture 11 about resultant of the general coplanar for systems, and I will first discuss the principles of the general coplanar concurrent for systems, and after that we'll have 13 examples to solve. First, we have resultant of coplanar for systems. So assuming we have coplanar concurrent forces, let's limit them to three first. Then we have to arrange them into tip to tail arrangement, and the resultant of the system is simply the one that will be represented by an arrow which is connected from the tail of the first force to the tip of the last force. So this is it. Then we have to resolve each force into their each components, namely Fx, F1x, and F1y. Then we have F2x and F2y, F3x and F3y for that case, and so on and so forth. There are more than three forces. Then this is the resultant. The resultant forms an angle with the positive x-axis called that theta x, and its components are namely r sub x and r sub y. So in this case, r is in the first quadrant, but it can be in second, third, fourth, or whichever quadrant. Then, from the figure, Rx is simply the sum of the x components of the individual forces in the system, or we call this summation forces x, and the components are positive if they are directed rightward, as in the given example, while Ry is simply the sum of the y components of all forces in the concurrent systems and coplanar systems. In this case, only F3y is negative, but in general, R sub y is summation forces along y. So therefore, this angle, theta x, can be obtained by, from trigo, we have a right triangle tangent theta x equals absolute value of Ry over Rx, absolute value of Rx. Then if the resultant is in the first quadrant, then that's the original value of theta x, and it is expected acute. Then the magnitude of r is square root of rx squared plus ry squared. And we have to expect four cases for the location of r. For case 1, in the first quadrant, theta x is simply r tan of absolute value of ry over rx in quadrant 1. While if it lies in second quadrant, this angle is the acute angle. If we make ry and rx both positive, so theta x is 180 degrees minus r tan of absolute value of ry over rx, and that is understood. Theta x is from the positive x-axis to the line of action of the resultant, and that's the standard form as in trigonometry. So in this case, rx is negative, ry is positive. Case 3, in the third quadrant, both rx and ry are negative, so theta x is 180 plus r tan of absolute value of ry over rx. Quadrant 3, then case 4, in quadrant 4, then theta x is 360 degrees minus r tan of absolute value of ry over rx. So in that case, ry is negative, rx is positive. For the position or value of r, if case 6, if r is vertical, then it means rx is 0 and ry is r. And case 6, if r is horizontal, means ry is 0 and rx is r for that case. And let's have the resultant of the general coplanar force systems. So this time, the forces are coplanar. We have P, Q, and T. Then, using axiom of mechanics 2, we can add a pair of equal forces acting at O. another pair of equal forces Q acting at O also, and another forces, a pair of equal forces T acting at O. Take note that by adding these pairs of equal forces that are in equilibrium, the original effect of the three forces is unaffected by the addition of these pairs of equal forces that are in equilibrium. So we take note that this P here, which is up to the right, and this P which is down to the left, which are parallel, constitute a couple. So this is also the P that is up to the right, now at O. But we replace these two forces, equal forces, by a couple which is clockwise. And we will denote that by C sub P. Then this Q here, the, which is down to the right, and this Q which is up to the left, constitute a couple which is counterclockwise. So we will remove them and replace them by a single couple C sub Q counterclockwise. Then finally, this T here, which is up to the left, and this T here, which is down to the right, constitute a couple, and they are, it is a couple, we can replace them by a couple which is counterclockwise, like that. Since there are two counterclockwise couples and only one clockwise couple, let's assume in our discussion here that the two couples have combined have greater magnitude compared to the clockwise couple. So since couples are independent of the moment center, we can move them anywhere on the plane of the forces or the plane of the couples, and we will denote them by C sub R. Same is true with these three concurrent forces. We can replace them by a single force R. So this system, the original system, is equivalent to this plus a resultant couple. And further, these three forces can be replaced by a single resultant. So we have two forces that are upward, one force that is downward, two forces that are rightward, and only one is leftward. Therefore, the resultant is, let's consider assumption again that since there are two upward forces and only one down forces, two rightward forces, only one leftward force, so therefore the resultant is up to the right. So we have a resultant acting at O, up to the right, and a couple which is counterclockwise, C sub R or MO. Then we can simplify this system further, unless otherwise it is the force and a couple that are required to replace the real system, and with the force acting at a specific point, specified point, then the original system can be reduced to this system. But there is a situation where we are only asked for the location of R from a certain point. So because the resultant is counterclockwise, in order for this resultant to produce counterclockwise moment about O, then it should be below O, and the inclination remains the same up to the right. Then we have to specify the perpendicular distance of that resultant from the point O. And in order to compute this perpendicular distance, note that the moment of the resultant about O is R times perpendicular distance, and that is counterclockwise. Therefore, that product R times perpendicular distance is equated to C sub R or MO. So from there, you can solve for D. There are also situations where it is the x-intercept or the y-intercept that is required. So for that case, we use Varignon's theorem, move the force along its line of action. So for instance, we want to find the x-intercept. So take note, the horizontal component of the resultant passes through the specified point. So we can compute the moment of Ry and about O, which is equal to Ry times x-intercept A. Then since that is counterclockwise, that is equated to C sub R or MO. Similarly, the moment of Rx about O, the component of R, Ry passes through O, is Rx times the y-intercept B, and it is also counterclockwise. So it is equated to the moment of the resultant, which is C sub R or MO. So C sub R or MO is also Ry times A. So from there you can solve for A. C sub R equals MO equals Rx times B. So from there you can solve for B. So that's it. So let's have this first example. The resultant of the two forces shown below is the force R with the magnitude and direction shown. So determine the magnitude of the forces P and F if the magnitude of R is 450 newtons. So that's the figure. So we have two forces here. The angles are known. We are here the direction of R in the first quadrant, and the magnitude is given. So therefore, Rx, which is summation forces X, is equal to 450 cosine 30. Ry, summation forces Y, is equal to 450 sine of 30. So to solve, Rx equals 450 cosine of 30, and that is equal to 389.7. So that is equated to the sum of the x components of these unknown forces P and Q. So 389 Ry on the other hand is 450 sine 30, so it is equal to 225 newtons. So 389.7, the x component resultant is P times 5 over 13 plus Q cosine 40. So this is the x component of P, the x component of 40 equated to the x component of the resultant. Likewise, P times 12 over 13, because this is 13, minus Q times sine 40 degrees equals 225. Equation 2. So solving these two equations simultaneously by elimination or substitution, we get P is 440.1 newtons and Q equals 286.3 newtons. So those are the values of P and Q. Example 11.2, four equal forces act on one corner of an inverted regular pentagon as shown. So determine the angle that the resultant forms with the horizontal. So given the figure and these forces are equal as stated in the problem, and take note this is a regular pentagon, so we will assume that each force is, you may assume it is equal to P, or so that because we can cancel P, so we'll just assume it is 1 kilonewton each. So again, we solve for the interior angles. There are 5 thetas, and the sum of interior angles of a polygon is given by n minus 2 times 180 degrees. So from there, we can solve for theta. So from the figure, because this triangle here and that triangle there are similar, so we will call this angle alpha, that's alpha, and we will show later that this angle is also alpha, but for the meantime, let's call that beta, because the regular pentagon can be inscribed in a circle, and we have the same subtended arc. That's the explanation from geometry, but we will not do that. So first, 5 theta equals n minus 2 times 180 degrees. So theta equals 108 degrees. Because this is an isosceles triangle, these two are equal, then a line that is perpendicular to this horizontal line here will bisect this angle. So this angle is theta over 2 or 54 degrees. So alpha equals, because this is horizontal vertical, so 90 degrees there, 90 minus 54 degrees. So alpha is 90 minus 54 degrees equals 36 degrees. So knowing alpha, we can now solve for beta. As expected, this is also 36 degrees because the entire angle here is theta or 108. So therefore, beta is 108 minus 2 times alpha, and alpha is 36 degrees. So it is also 36 degrees. So let's compute Rx, summation forces X. So take note that this force makes an angle of 72, alpha and beta, and because they are equal. This one is 36. This one is also 36. So Rx is 1 times cosine 72 plus 1 cosine 36 plus 1 cosine 36 plus 1. 1 and 1 cosine 36. So R sub x is equal to 2.927 kilonewtons. Then summation versus y equals Ry. So we have 1 sine of 72 plus 1 sine of 36 minus 1 sine of 36. So it is just sine 72. So tangent of theta x or tangent of theta of the resultant is equal to Ry, absolute value of Ry over Rx. Because both components are positive, obviously the resultant is in the first quadrant. So theta x is equal to 18 degrees up to the right from the horizontal. So next, let's have example 11.3. For the concurrent force system shown below, determine the resultant force. So given the figure, so we have to solve by computing the x component, Rx. So Rx equals 240 cosine 33 minus 130 times 5 over 13. This is 13. Then minus 360 times 4 over 5 because this is supposedly 5. And this has no x component. So that's the x component of the resultant, negative 136.7 newtons. Ry is 240 sine 33 plus 130 times 12 over 13 minus 360 times 3 over 5 minus 180. So solving for Ry is equal to negative 145.3 newtons. So then we can now answer the question resultant of the system. So we may write the resultant in vector form. So it is negative 136.7 I negative 145.3 J Newton. So that's the resultant. In some cases, you might be required to specify the magnitude and its direction. So let's continue. R is square root of 136.7 square plus 145.3 square. And take note that both components are negative, so the resultant lies in the third quadrant. And the angle it makes with the positive x-axis is 180 plus r tan of absolute value of Ry over Rx. So the magnitude is 199.5 newtons down to the left at an angle theta x equals 180 plus r tan of absolute value 145.3 over 136.7. So that would be 226.7 degrees. So this is also the alternate answer to that problem. Example 11.4. For the beam shown, determine the required tension in table BC if the resultant of the three forces exerted at point B is to be vertical. So what is the corresponding magnitude of the resultant? So this is the figure. Then take note that the resultant is to be vertical, and because there are two active forces, the tension is only passive force, so we expect that the resultant is downward. So Rx is 0 because the resultant is vertical downward, so to make it clear. So we begin by this equation, Rx is 0. So we have 15.6 times 12 over 13. So 15.6 times 12 over 13, that's Rx equals 0. Minus 10 times 3 over 5 minus tension times 4.2 over 5.8 because the length distance known equals 0. So we have to compute for T from this equation, which is the only unknown. So T is 11.6 kilonewtons. Then for the second part, summation forces Y equals R. So downward, we expect that R is downward. So R is 15.6. By the way, this distance is 4 for the vertical component of T. So square root of 5.8 square minus 4.2 square is 4 meters. So Ry, which is downward, is 15.6 times 5 over 13. Let's make downward positive. Plus 10 times 4 over 5. Then minus 11.6 times 4 over 5.8. So solving for R, which is also Ry, it is 6 kilonewtons. 11.5, determine the required tension in cable AC, knowing that the resultant of the three forces exerted at point C of the boom BC must be directed along BC. The corresponding magnitude of the resultant. So this is the figure and the given data. So we can solve this easily if we rotate the axis. But before that, let's solve for the angles. So this angle is 180 minus 35 minus 65. So this is 80 degrees. Let's call that theta first. This angle is 35 degrees also because that's 35. So theta is 180 minus 65 minus 35 degrees. So theta is 80 degrees as expected. Then this is the, let's call this the V axis, which is perpendicular to boom BC. And BC is the U axis. So that's the direction of R, expected R, because all forces are going in this direction. So that's 90 degrees, V and R. Then that's also 35 degrees. So that we can solve for the tension, we have to sum up forces along V equals 0. So going in that direction positive, so this is the V component of tension is T sine of 80, then minus 100 sine of 35 minus 150 sine of 60. 35 plus 25 is 60. R has no component because it is perpendicular to the V axis. So solving for the tension, it is 190.2 newtons. Then summation forces along the V axis, the U axis rather. So RU equals R, and all forces are in this direction. So they are treated positive. So R equals, let's begin with tension, 190.2 cosine of 80 plus 100 cosine 35 plus 150 cosine 60. So that is equal to R. So R therefore is equal to 189.9 newtons. Let's proceed to 11.6. The force system shown below has a resultant of 500 newtons pointing up along the y-axis. Compute the value of F and theta. So this is the situation. The resultant is 500 newtons magnitude and it is pointing along the y-axis upward. So let's put the resultant first so that we can analyze that Rx is 0. Summation versus x is Rx equals 0. So F cosine theta, positive, plus 600 cosine 30, then minus 1,200 equals 0. So simplifying, F cosine theta equals 730.4. Call that equation 1. Summation versus y equals R, and R is 500. So F sine theta minus 600 sine 30 equals 500 because this has no y component. So F sine theta equals 800. So dividing equation 2 by equation 1, F sine theta over F cosine theta equals 800 over 730.4. We can cancel F. Tangent theta is equal to 800 over 730.4. So theta is equal to 47.60 degrees. Substitute into equation 2 to solve for F. F sine of 47.6 equals 800. So the magnitude of F is 1083 newtons. Example 11.7. The three forces act on the bracket shown below. Determine the magnitude and direction theta of P so that the resultant force is directed along the positive U axis and has a magnitude of 1500 newtons. So this is the figure. Again, we can rotate the axis. You may also not, but let's rotate the axis. So because this is 30 degrees, the line or the axis perpendicular to this u-axis forms an angle also of 30 degrees with the y-axis. Since everything is given, then RU is equal to 1500. That's given. Then this is the v-axis perpendicular to the u-axis. This angle here is 30 degrees. So since this is 45, that is also 45. So therefore, this angle here not shown, but it is 50 degrees. RV is equal to 0, of course. So RV is equal to 675 cosine of, as I said, 15 degrees, and plus 300 uh, sine of 30, because this is 30 degrees, it is positive, pointing the positive v-axis. Then minus p sine of theta equals 0. So set up the first equation, p sine theta. So that's R, 1500 newtons the magnitude. So p sine theta is 802, call that equation 1. And summation forces along U equals R, and R is 1500. All of these forces are positive. So 675 sine of 15 in this direction, because it's 15 plus 300 cosine 30, then plus p cosine of theta equals 1500. So p cosine theta is 1065, equation 2. So divide equation 1 by equation 2 to solve for theta. So p sine theta over p cosine theta is 802 over 1065. So tangent theta is equal to 802 over 1065. So theta equals 36.98 degrees. Substitute into equation 1, p sine of 36.87 equals 802. So p is 1333 newtons. So another way, let's just use the x and the y axis. Summation forces x is Rx because R is given. So Rx is 1500 cosine 30, and that is equal to Px, x component of P, then plus 300 plus 675 cosine 45. So Px is equal to 521.7. Summation forces y equals 0. Let's call the component of P as Py. So it's the y component is negative 1500, negative 1500 sine 30 equals 675 sine 45, then minus Py. So Py is 1227 newtons. So the magnitude of P is square root of 521.7 square plus 1227 square. That is same, 1333 newtons. Then for theta, uh, to solve for theta, tangent of uh, 30 degrees plus theta is Py over Px. Let's just make them positive because it's positive here, although do not mind the resultant that lies in the fourth quadrant. Just treat this as a right triangle, Px and Py. So theta is arctan of 1227 divided by 521.7 minus 30 degrees. So theta is 36.97. So they are practically the same. Example 11.8. The block shown below is acted on by its own weight, W 300 newtons, an horizontal force F 450 newtons, and the pressure P exerted by the inclined plane. The resultant of these forces is parallel to the incline. Determine P and R. Does the block move up or down? So this is the figure. Again, let's solve this by rotating the axis because the resultant is parallel to the incline. And because 450 and 300 are the active forces, and this is high, so we expect that the resultant is up to the right, parallel to the incline. So the resultant is there. Then let's make an axis perpendicular to U, which is the V axis. So Therefore, the angle of inclination is 30 degrees. The angle between the vertical and the normal or perpendicular to the incline is also 30 degrees. So that's 30, this is 30 degrees given, that's 30 degrees. This is 30 degrees. So therefore, this is 15 degrees. So summation forces along V equals 0. R sub V is 0. And that is P cosine of 15. This is up. Then minus 300 cosine of 30. Minus 450 sine of 30. Then simplifying, we can now solve for P. P is 501.9 newtons and it is up to the left with an angle with a vertical of 45 degrees. Then summation forces along U equals R. Then it is 450 cosine of 30 minus 300 sine 30 minus 501.9 sine of 15. This is negative in this direction. So R is equal to 109.8 newtons. So since our assumed direction for R is correct and it is positive, then to answer, does the block move up or down? Of course, it will move up the incline. Sample 11.9, the two springs shown in the figure are identical with normal lengths to 50 mm and spring constants K. So same K, because they're identical. The sum of the masses of blocks A and B is 20 kilograms. So though they are identical, it doesn't mean that their masses are equal. So determine the values of K and the masses of the blocks. So given the figure is given, then we have to draw the free body diagram of block B. Remember that the tension in the spring is the spring constant times the displacement, delta S. So this tension is equal to K times delta SB. We have the weight of B, which is mass of B times acceleration due to gravity. Then tension T sub B, K times delta SB, where delta SB is 280 minus normal length 250. So delta SB is 30 mm. Summation versus Y equals 0. So that means, because this is in equilibrium, so no resultant. So K delta SB, K times 30 equals MB times G, or minus MB times D equals 0, equation 1. Then let's draw the free body diagram of A. So let's transmit. We have here mass of A times G and the tension, which is 30K or K30. Then tension in the spring above A is equal to K times delta SA. And delta SA is 300 minus 250. Then summation versus Y equals 0. So K times 50 minus MA times G minus K times 30 equals 0. So from equation, or from this equation, we have K times 20 equals MAG. So that means K is MAG over 20. So let's substitute this value of K here in equation 1. So MAG over 20 minus MB times 30 minus MBG equals 0. So we can cancel G, the acceleration due to gravity, and take note that MB is 20 minus MA. So we have 1.530 over 20, 1.5 MA minus quantity 20 minus MA equals 0. So MA is 20 divided by 2.5, so MA equals 8 kilograms. Therefore, MB is 20 minus 8, so 12 kilograms. Then the spring constant in this equation here is 8 times 9.81 over 20. So K is 3.924 newtons per mm. If we replace, if we multiply 100 mm per meter, then it is 3,924 newtons per meter. So either way, you may answer 3.924 newton per mm or 3,924 newtons per mm. That's still acceptable. Sample 11.10, two locomotives on opposite banks of a canal pull a vessel moving parallel to the banks by means of two horizontal ropes. The tensions in these ropes are 8 kilonewtons and 9.6 kilonewtons, while the angle between them is 60 degrees. Find the resultant pull on the vessel and the angle between each of the ropes and the resultant force. So this is the given figure. Then let's do the parallelogram forming these two given tension loads and the resultant, of course, the main diagonal. So that's 8 kilonewtons, 9.6 kilonewtons, then the resultant, of course. This is also 9.6. We will call the angle that the resultant makes with the 9.6 kilonewton tension as alpha, resultant and the 8 kilonewton tension as beta. Take note that alpha plus beta is 60 degrees, and take note also that this is alpha. So therefore, this remaining angle here is 120 minus alpha minus beta, or 120 minus 60 is, 180 degrees minus quantity alpha plus beta, and alpha plus beta is 60, so this is 120 degrees. So by cosine law, in this right portion triangle, we can compute r. So by cosine law, r square equals 8 square plus 9.6 square minus 2 times 8, 9.6 cosine of 120 degrees. So solving for the magnitude of r is 15.26 kilonewtons. Then by sine law, we expect alpha is small because alpha plus beta is 60, so nothing to worry about applying sine. So 8 as to sine alpha equals 9.6 as to sine beta equals 15.26 as to sine 120. So alpha is 27 degrees, beta is 32 degrees. So the 9.6 kilonewton force makes 27 degrees with the resultant, and the 8 kilonewton tension force makes 32 degrees with the resultant. Sample 11.11, the top of the fixed tower shown is subjected to a horizontal force of 75 kilonewtons and a tension P in the heavy flexible cable, which is tightened by the power winch P. If the net effect of the two forces is to produce a downward compression of 45 kilonewtons on the tower at A, determine the tension T in the cable and the angle theta made by the cable with the horizontal. So this is the figure. So we have 30 kilonewtons, we have 75 kilonewtons at A horizontal, then there is a downward force 45 kilonewtons compression, then we have the tension which is down to the left, making an angle theta with the horizontal. So since the 75 kilonewton and the 45 kilonewton forces are perpendicular to each other, although this is the resultant, net resultant, so we form this side, we form a parallelogram, that one, and therefore this is the tension T, which makes theta with the horizontal. This is also T, so that's theta also there, and this is also T. So from the figure, we can now solve for T, square root of 75 square plus 45 square. So the tension force is 87.46, and theta, tangent theta, is 45 over 75. So theta can also be solved easily, 30.96 degrees. Sample 11.12. The force table shown below is used to demonstrating the parallelogram law for addition of forces. The system of strings and masses will be stationary only if the resultant force acting on the junction of the string vanishes or zero. Resultant is zero, so Rx 0, Ry 0. So calculate the angles alpha and beta that would produce this state of equilibrium if the forces in the string have the magnitude shown, or the masses attached as shown. So because the resultant is 0, that means if we draw the force triangle, it forms a triangle. The three forces must close. So the tension in this string is 5G. So let's say 5G, and the angle it makes with the horizontal, let's make 8G tension as the horizontal. Then next is this one, 6G, and as I said, let's make the tension in this string as 8G horizontal. So this is, I'll call this theta 1, then this one theta 2. So theta 1 and theta 2 are important. The third angle is not important. So for the free body diagram of the point of intersection, so we have 5G up to the left, and that angle is theta 1, the horizontal, then 6G down to the left with angle of theta 2, and this is 8G. So that means this alpha is 180 minus theta 1, and this beta is 180 degrees minus theta 2. Since Ry is 0, 5G sine theta 1 equals 6G sine of theta 2. But actually, we can solve for theta 1 by law of cosines. So 6G square equals 8G square plus 5G square minus 2, 8G, 5G cosine of theta 1. Cancel out G square, common to all terms. Then use your calculator. Theta 1 would be 48.51 degrees. So alpha is now 180 minus 48.51 degrees. So alpha is equal to 131.49 degrees. Likewise, by sine law for theta 2, so 5G over sine theta 2 equals 6G over sine of theta 1. So solving for theta 2 is 38.63 degrees. So beta is 180 minus 38.63. So beta equals 141.47 degrees. Example 11.13. This is our last example. The three concurrent forces acting on the post produce a resultant force Fr equals 0, so the resultant is 0. If F2 is half of F1 and F1 is to be 90 degrees from F2 as shown in the figure, determine the required magnitude of F3 in terms of F1 and the angle theta. So this problem is almost similar to this. So let's draw the this free body diagram of the point. So alpha plus beta is 90 degrees. That's given. So since Fr is 0, so Fy is 0. So that is F2 sine alpha minus F1 sine beta equals 0. So Newton forces Y equals 0. So F2 sine alpha minus F1 sine or beta equals 0. So replacing F1, this is equal to 2 times F2 and beta by 90 degrees minus alpha. Transpose, so 2F2, F1 is 2F2 from this relation, and beta is 90 degrees minus alpha. So we cancel F2 and take note that sine of 90 minus alpha is cosine of alpha. So 2 cosine alpha, tangent alpha is 2, so alpha is 63.435 degrees. So that means beta is 90 minus 63.45 equals beta is 26.565 degrees. So from there, we can now solve theta, 180 minus alpha, minus 63.45 degrees. So theta is 116.565 degrees. That's our answer for angle theta. And for F3 in terms of F1, summation forces X equals 0. Because resultant is 0, Rx is 0. So from the figure, F3 equals F1 cosine of 26.565 minus F2, which is F1 over 2 or 0.5 of F1 cosine of alpha, which is 63.45. So we can now express F3 in terms of F1, and it is 1.118 of F1. So that's all for this lecture series 11. And I hope that you can follow all the solutions I presented here, and I hope that these problems will help you in your studies. So don't forget to subscribe and comment in the comment section. Thank you.